Let's begin with the following system for x and y. I would like to analyze the equilibrium point 0, 0, so I'm going to find the linearization of the system near that point. I'm going to have to take derivatives, so I'm going to simplify these equations so that dx dt is equal to y minus x cubed minus xy squared plus 4x. And dy dt is minus x squared y minus y cubed plus 4y. I'm now going to find the Jacobian matrix. So the first entry in that matrix is going to be the derivative of the first equation with respect to x. That's going to be minus 3x squared minus y squared plus 4. Then I'll take the derivative of the first equation with respect to y, which I will get 1 minus 2xy. Now I want to take the derivative of the second equation with respect to x, and I will get minus 1 minus 2xy. And then finally, the derivative of the second equation with respect to y is minus x squared minus 3y squared plus 4. I'm specifically interested in this Jacobian near the equilibrium point, or at the equilibrium point 0, 0. So when both x and y are 0, I get the matrix 4, 1, negative 1, 4. I'm going to try to figure out the eigenvalues for this system, so I'm going to take the determinant of j minus lambda I. That's going to equal 4 minus lambda times 4 minus lambda, or 4 minus lambda squared, plus 1. And if I expand that out, I'm going to get lambda squared minus 8 lambda plus 16, and plus 1 gives me plus 17. I'm going to set that determinant equal to 0. Oh, well, in this case, I'm going to use the quadratic formula so that lambda equals 8 plus or minus the square root of 8 squared, which is 64, minus 4 times 1 times 17. And I'm going to divide that whole thing by 2. So this simplifies down to 4 plus or minus I. Now we can see that because we have two complex eigenvalues and the real part is positive, that this should be a spiral source. And because that's a generic equilibrium point, we can conclude that the nonlinear system is, again, a spiral source. So let's confirm that by looking at what's going on in slopes. So here is our system, and we can look near the equilibrium point 0, 0. So I'm going to zoom in, and I'm going to pick a couple solutions near the equilibrium point, and I can see that those solutions are spiraling away from 0, 0. So we do have a spiral source. But if I zoom back out, you'll notice that these solutions do not spiral out forever. They seem to be collecting near some sort of circle of radius 2. So knowing that the equilibrium is a spiral source isn't really telling me everything about this system. There's something that's going on in this region of a circle of radius 2 centered at the origin. And we want to be able to figure this out as well. So I'm going to go back to my system, and what I would like to do is consider what happens when I change a system to polar coordinates. I see some sort of circular behavior, so I really want to know what's going on in polar coordinates. So I'm going to consider a change of coordinates. I'm going to let x be r cosine theta and y be r sine theta. And what I want to do is I want to find dx dt and dy dt in terms of r and theta, and possibly dr dt and d theta dt. So let's see what dx dt is if I think about r and theta as functions of t. Well, since x is equal to r theta, I have to use the product rule. So this becomes dr dt cosine theta minus, and then r is going to get left alone, and then I take the derivative of cosine theta, I get a minus sine theta times d theta dt. Now let's see what happens with dy dt. Okay, y is equal to r sine theta. So using the product rule, I get that dr dt is multiplied by sine theta. And for the second term, I'm going to get a plus, r is left alone, and the derivative of sine theta is cosine theta, again, times d theta dt. Now, I don't see anything in particular from finding dx dt and dy dt, but I'm going to take some what look like strange combinations of x and dx dt and y and dy dt to figure out if I can simplify these derivatives at all. So I'm going to do x times dx dt plus y times dy dt and see what happens. When I do that, I'm going to remember that x is equal to r cosine theta and y is equal to r sine theta. So if I multiply the first equation, this one, I'm going to multiply by x equals r cosine theta. Then what I should get is r dr dt cosine squared theta minus r squared sine theta cosine theta d theta dt. And then I'm going to multiply that second equation by y equals r sine theta. And what that's going to become is, let's see, this will become plus r dr dt sine squared theta plus r squared sine theta cosine theta d theta dt. And when I notice if I add up x dx dt and y dy dt, I see that the second and fourth terms cancel, and I have a cosine squared and a sine squared in the first and third terms that add up to 1, and I just get r dr dt. And so now I have this relationship that r dr dt is equal to x dx dt plus y dy dt. Well, that's interesting. Let's try something similar. Let's try x dy dt minus y dx dt. So x dy dt minus y dx dt. Well, in this case, I'm going to multiply the dy dt equation by x and the x dx dt equation by y. So let's see what happens when we do that multiplication. So x times dy dt is going to give me an r dr dt sine theta cosine theta plus r squared cosine squared theta d theta dt. And then when I subtract y times dx dt, I'm going to get a minus r dr dt sine theta cosine theta. And then I'm going to get minus a negative, so a plus, and this will be r squared sine squared theta d theta dt. And again, I have that the first and third terms cancel, and then I see a cosine squared and a sine squared in the second and the fourth terms. And so I get that these add up to r squared d theta dt. And that tells me r squared d theta dt is equal to x dy dt minus y dx dt. So I can kind of summarize these things. Let's see. I've learned now that r dr dt is equal to x dx dt plus y dy dt. And I've also learned that r squared d theta dt is equal to x dy dt minus y dx dt. And so really, I now have a way to figure out what dr dt and d theta dt are in terms of x's and y's.